Right, okay. Hello everyone. I just wanted to quickly clarify a few things because they will make it they will start making it clear on Show My Homework, but I wanted to clarify with you guys as well. In terms of handing work in to us as a science department, um, you don't need to hand in any sort of additional things that you do, like your review and transforms or anything. The only thing that you're going to be submitting is your assessments, your topic tests that um, are set every 2 weeks, and then you have 2 weeks to do, and then you have another one. The only time I would ask to check like what revision you've been doing is if you like completely bomb the topic test, which I'm sure none of you guys here would be doing. So like, I don't want anyone here to be stressing out about submitting loads and loads of work to the science department. You're mainly just submitting those topic tests, okay? Right, so back on track now. We are going to be starting our new topic, which is the atomic structure and the periodic table topic. We've already covered atomic structure in class, what a proton is, what a neutron is, electron, etc. But I'm going to be doing a quick recap of that because that was a few months ago. So I'll be recapping that and then leading that into the periodic table, which you guys are going to be assessed on. So here we go. Right, so atomic structure. Just as a quick recap, the main key thing that you do have to be aware of when it comes to atomic structure are the three main what we call subatomic particles. So subatomic, if you think about what sub means, like submarine, um, anything like that, it's all to do with underneath. So basically, subatomic is particles are particles that make up inside of an atom. Okay, so here we have an atom. Hopefully we remember this structure. Let's say we have this. Ooh, excuse my wobbly circles. Okay, this is my oblong shaped atom. Pretend that they are circles. Pretend. What I want you to be able to do is basically label this and extract as much information as you can from this diagram, no matter how garbage the diagram looks, be able to decipher it. Now, the first thing I want us to remember is that there are two main locations inside an atom. So this whole thing is an atom here. The first location I want you to be aware of is this center, and remember we called the center of the atom the nucleus. And it has two subatomic particles that are in the nucleus. The first one is what we call the proton. And it has a charge, it is positively charged. The way I remember this is if you think about like pro, when you're pro something, you're for it, and that's like being positive, isn't it? So pro is positive. And then, so these positive charges here, we have 1, 2, and 3 protons. So in this case, we have 3 protons. And we have other circles here, 1, 2, 3, 4, that don't have a charge on it. They have zero charge. They're completely neutral in terms of their charge. And we call these particles neutrons. Neutrons being neutral. I'm just going to put 0 there as in zero charge. And in this case, we have 4. Now the outside rings around my nucleus, so there's ring number 1 and then ring number 2, so number 1 and number 2. These are what's known as the electron shells. And they have only one subatomic particle that live there. And that subatomic particle is known as the electron. And those are negatively charged. In this case, we have 1, 2, and 3. The first thing I want you to notice, okay, is that the number of protons, we have 3 here, and the number of electrons is balanced. And this makes sense because the number of protons represents how many positive charges we have. So if we have 3 protons, we're going to have 3 positive charges. Louis, this is just a quick recap of what you've already done in class, so you should already have your notes somewhere in your book. But I will also put the booklet back up on the website in a second. But I just want to do a quick recap because you do need to know this for our topic, which is the periodic table topic, and that's going to be new. So that is already on the website. Let me just link it real quick. So there are notes for the periodic table there now, but this is just a quick recap of what we'd already done in class. If you want to make some notes now, you can use it on some paper, lined paper or something. Okay. So one subatomic particle, in this case there are 3 electrons. Okay. So we have 3 positive charges. And if we have 3 positive charges, but we want to balance that out, we're going to need to have 3 negative charges to balance that out. So in a stable, sort of normal atom, protons equals electrons. Basically, the number of how many protons, positives we have, is going to equal to the number of negatives that we have. The number of neutrons, that can change quite easily because they don't contribute a charge themselves. So it's not like it's going to be hard to add a neutron, to have an extra neutron, because it doesn't imbalance it at all. Like, for example, in this case, we have 4 neutrons. Well, that doesn't make the charge imbalanced, so that's still okay. Right. So that is the general structure of the atom. Now we want to look at the roles and responsibilities of each subatomic particle. Okay? So this hopefully is just recap. I'm going to give you a link now to a periodic table, and I want everyone to be able to have it open because it is very, very important for us to be able to read the periodic table. I'm going to link you to the AQA version. The reason why is because it's best for you to you know, to be comfortable with the AQA version of the periodic table, because there are many, many versions online, but this is going to be the one that you see on your test. Where is it? Sorry, I'm just getting the link to a bigger version. There we go. So if you click that link that I've just sent over now, I would click the rotate button as well, just so then you don't have to adjust your head to be able to read it. But you notice that the periodic table has some numbers on it. And these numbers do represent the number of protons, the number of neutrons, and the number of electrons. So we can figure out how many of each subatomic particle we have through looking at the periodic table. And this is quite important and something that you'll need to be able to do, because we're not going to, like, no exam board is going to ask you to actually be able to memorize the number of protons, neutrons, and electrons for any of the elements, right? We just want you to be able to find that information using the periodic table. Now let me just get this up on my screen so you can see. Hold on. Display. Okay. Right. So hopefully we all see my screen now. Here is our periodic table. Now, if you notice, we have at the very top of our periodic table, we have a key. That key will be provided for you. Make sure you look at the key if you don't remember which number is what. At the very top here, notice it says relative atomic mass. That's basically the mass of the atom. Then we have our symbol, then we have our name, and then the very bottom number, so the number at the bottom, is our atomic brackets proton number. So the bottom number in each of these little rectangles, each of these little blocks for each element, represents how many protons that element has. So for example, lithium has 3 protons, palladium has 46, mercury has 80. That bottom number represents how many protons, so how many positive charges that element has. Now, because you know that the number of negative charges has to balance the number of positive charges, we also can then say that the bottom number also is going to be the same as the number of electrons we have if the atom is balanced. So for example, in a lithium with balanced charges that overall has no charge, we're going to have 3 protons, but I also know that there are going to be 3 electrons. For iron, I know there's 26 protons from this number, but there's also 26 electrons. Now, back to our table. The number of proton is a really, really important part of an atom. I mean, all of them are important, but the proton, in my opinion, it is It is huge. And the reason why is because the number of protons determines the element. So theoretically, if you were to change the number of protons you had, theoretically, if you had iron, say, that has 26 protons, and somehow in a laboratory you were able to stick another proton in, add another proton to iron, one more, that iron would turn into cobalt. And I know that seems a bit magic, but that is actually how it works, because the number of protons determines what element something is. It's unique to each element. And I don't want you to do this, but just to prove it to you, if you went through every single block in this periodic table, every single element in this periodic table, you will not find a bottom number, atomic proton number, that is the same. So for example, cobalt has 27 protons. Only cobalt has 27 protons, nothing else. If you made something, if you gave a proton to iron to make it 27, it will turn into cobalt. If you took away a proton from nickel, it will turn into cobalt. So the number of protons something has determines the element. And I think that's actually pretty crazy, because if you think about it, these elements we see from like our point of view, huge differences between them. Like for example, let's have a look where Mercury is. For example, Mercury and gold, they seem totally different, right? Gold is this yellow, shiny, solid substance, solid metal, and then Mercury is like the silver liquid at room temperature. But the only difference is one proton. So theoretically, if you were able to remove a proton from our Mercury, you'd be able to turn it into gold. You would be able to. I mean, removing and adding protons, I say that, it is actually really, really difficult to do. So it's not one of those things where you have a go at it at home, because the nucleus is bound together so strongly. But theoretically, you can. And what we have done previously is we have actually created new elements in laboratories by smashing atoms together in high speeds and hoping that some of the protons end up combining and sticking together to become a new proton number to create a new element. And we have actually done that many, many times. Many of our elements at the near bottom of the periodic table were built only in a lab by smashing atoms together and hoping that we make a new proton number. So the proton number basically is a big deal. It determines what element it's going to be. Just a recap, it is positive charge. And this is something that I want to add on. Remember, this is all recap. It has a relative atomic mass of 1. Right, so what does relative atomic mass mean? That's the big question. Relative atomic mass is, and you'll see on the periodic table, it's that big number at the top, but what does that big number at the top mean? So you'll see on the periodic table relative atomic mass. So lithium has a relative atomic mass of 7. Beryllium has a relative atomic mass of 9. That top number is relative atomic mass. But now, what does that mean? Let me just quickly switch over to window capture. Okay. What relative atomic mass means, is basically, in reality, our proton weighs very, 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 very little. But scientists, sometimes we like to make things easy for ourselves. We don't like to use very, very small or very, very large numbers that are hard to work with. So in reality, you don't need to memorize this number, but in reality, our proton has a mass of 1.67 times 10 to the minus 27 kilograms. 1.67 times 10 to the minus 27 kilograms. Now, imagine being a chemist and you're weighing out how many chemicals you need, and you're working with a number like that. It'd be annoying, wouldn't it? So we're saying, right, scratch that. We're not going to use its proper mass in kilograms. We're going to make a new unit that basically just compares our subatomic particles to each other. So we've decided the proton has a mass of 1. That new unit is called AMU. So it has a new mass of 1. We're going to drop kilograms because if we work in kilograms, we're going to get these crazy numbers. We're going to say a proton has a mass of 1. And we also notice that the neutron actually does weigh pretty much nearly exactly the same as a proton. So the neutron weighs nearly exactly the same as a proton. So we decided, okay, makes things easier. Relative atomic mass of a neutron is also 1. And then we looked at how much electrons are in terms of mass compared to our protons and our neutrons, and we realized that it was like 1/2000th of a proton, meaning it's so small, the electrons are so small that the weight is just very close to 0. So we decided to make it easy for ourselves, that it's so small we're not going to even bother counting it. And if this seems lazy to you, it is. It is lazy, but it makes things like calculations so much easier. So instead of working in like kilograms when it comes to atoms and things, we often work in what's known as relative atomic mass, shortened to AMU. Proton is 1, neutron is 1, electron is 0. So because of that, if you look back on the periodic table, that number at the top, that relative atomic mass, that means that the relative atomic mass is only going to include the number of protons plus the number of neutrons. How many electrons we have are not going to contribute to how much mass our atom has at all, because it's so small that it doesn't matter. One analogy I like to use is, let's take your whole weight, and you decide you want to lose some weight. And to lose some weight, instead of doing exercising, eating less, whatever, you decide, right, my hair has a little bit of weight, it weighs something, so I'm going to get a haircut, and then that means I've lost some weight. Well, technically, yeah, but the weight of your hair is so small it doesn't actually count. It's not going to make any huge difference to the overall you. Same case with the atom. Yes, the electrons weigh something, so it would be incorrect if you said electrons don't weigh anything. So do not say electrons don't have mass or don't weigh anything. Do not say something like that, because that would be incorrect. It does, but it's just so small that we just don't even care about it. Okay. Now, the neutron doesn't determine any charge, but because it does have a mass, it contributes to the relative atomic mass. So basically, on our periodic table, we can work out how many neutrons we have if we know how much the whole thing weighs and we know how many protons we have. So for example, with our atom here, our lithium, on the periodic table, it's 7 lithium 3. The 7 is its relative atomic mass. And our 3 is our proton number. So if it has a mass of 7, has 3 protons, then that means the other four are going to be neutrons because they're going to add up to the total mass. Remember, we don't count electrons because they're not really worth much at all. So the neutrons contribute to the relative atomic mass, and it has a neutral, so 0 charge. Now the electron, we're going to lead this into our periodic table topic now. The electron also has a very, very important role when it comes to our atom. It has a huge role. And the electron determines chemical reactions and bonding. Negative minus charge. This is how I remember what the electron. Sorry, my microphone cut off there. This is how I memorize what the electron does. Notice where the electrons are on our atom. They're on the outside. The nucleus is tucked in the center. Then there's a whole bunch of empty space, and then the electrons are the outside. So when it comes to a chemical reaction, where one element reacts with another element, so they have that interaction, what bits are actually going to be in contact with each other? Well, the electrons, right? The two nucleus of two separate elements that are about to do a chemical reaction aren't really ever going to meet. They're at the very center, hidden away. But what does meet are the electrons. So whenever you have a chemical reaction, whenever you have any bonding, whenever you have anything like that, in chemistry, it's always the electrons doing it. So the electrons have a very, very important role in shaping how these chemicals react with each other because they're the ones on the outside. They're going to be the ones that actually interact. The nucleus is not really going to be involved because it's at the very center. It's hidden away. So the electrons determine the chemical reactions. So, now leading us into our periodic table topic then. When it comes to our elements, we often see a pattern of behavior for our elements depending on the number of electrons we have. Let me switch my screen over. There we go. Hopefully that works. Right. So this booklet is available on the website that I just linked earlier. Remember, there is a Word document format for it, for you to type things in, or you can use a PDF format. It's up to you which one you want to use. I'm going to be doing the triple award topic. It's all pretty much the same as a double award, except at the very end there's something extra that we're going to do another day. So if you have chosen not to do triple award next year, if you're in year 9, then don't worry about it. I will tell you before we get to it, this is triple award stuff now. But right now, this is for everyone. So, a bit of history then. And I know hopefully some of you guys like history. I personally really enjoy scientific history. The 1800s was a huge time in science because our technology improved. Like we have the microscope now, we have different ways to do experiments now. So at this time, scientific knowledge is advancing. And part of this was discovering more and more elements. So the number of elements that we knew about at this time effectively doubled. And when we got to a point where there were around like 60 known elements ish, the lead scientists of the time decided, right, we probably need to organize all of these elements. Because before, there were very few elements that we knew about, so we didn't really feel the need to organize it. But then eventually got to a point where it's like, okay, hang on, we need to find some organization for this now. So the first person, not he probably isn't the first person to try, but the first sort of major breakthrough in terms of organizing the elements was a man named John Dalton. Um, if you have a really good memory back from Key Stage 3, you would have talked about John Dalton before. He's sort of known as the father of chemistry. No relation to Mrs. Dalton, assistant principal. I believe. So, John Dalton, he decided that he was going to organize the elements in order of their atomic weight. Notice that I didn't say mass because they didn't measure things in mass only at the time. They measured in weight using proper like weighing scales instead of electronic balances. And there is a small difference between mass and weight. That we're going to go into in another topic, but right now I do want you to be aware that it is just he organized them from atomic weight. So he put it from the lightest element to the heaviest element. That's what he did. So he organized it in terms of atomic weight. John Newlands did the same thing, so he also organized it with atomic weight. This is after Dalton now. He thought that's a pretty good idea. Let's organize it in terms of weight. But then he also noticed something. He noticed that every 8 elements, there was a pattern in terms of their of bonding and reactivity. So for example, he noticed that every 8th element is super reactive in water. Every 8th element is the next set of every 8th element is unreactive. He noticed like a pattern. If you imagine it to be like, for example, the first one, the 8th one, and then the 16th one, and then the 24th one behave similarly. The second one, the 10th one, the 18th one behave similarly. So basically, like, there was a pattern where every 8th, after he organized it in weight, every 8th element shared similar properties with the element 8 down the line. Hopefully that makes sense. He called this the Law of Octaves, where he noticed that pattern. So pattern of every 8 elements. However, there was a problem with John Newlands, a problem so huge that the scientific community sort of laughed at him literally and said, you know, they didn't say, John Newlands, you suck, but effectively they said that because after the element calcium on the periodic table, after calcium, that pattern broke down. So his pattern only worked for the very beginning, but then stopped working for the heavier elements. And he couldn't really explain why, so they thought, okay, John Newlands, you're talking nonsense, we're going to ignore you now. So stopped working for heavy elements. The reason why John Newlands was wrong is he made a key mistake, a very, very huge mistake, in fact, in that he thought at his time they already discovered every single element. That was his big mistake. He thought they all had already discovered everything, so when he organized them into weight and said that there is a pattern, well, of course it's going to stop working because there are elements that are missing from what he knew about. So it stopped working eventually because there were elements there that he didn't know of that would have fit the pattern if he only did what Dmitri Mendeleev did. Now, Dmitri Mendeleev is known as the father of the periodic table because it is his version that we use because he did it properly. Even though the two guys before attempted to organize the periodic table, they didn't do as great of a job as Dmitri Mendeleev did. And the key thing about Dmitri Mendeleev is that he did pretty much the same exact thing as John Newlands, organize them by atomic weight, notice the pattern, but he left gaps. Now let me tell you now, this is a very common exam question of what did Dmitri Mendeleev do that made his periodic table the successful one, and that was because he left gaps. So the story goes is that whenever Dmitri Mendeleev was taking the train to work, he had each element on like a playing card, and he would organize the elements on the train with these cards, and then he noticed that pattern emerging, same as John Newlands did, but then he decided, right, hang on, this one didn't fit a pattern. Maybe there was an unknown element that we didn't really know about yet that would fit that spot instead, and maybe this instead would go somewhere else. So that's what he did. He left gaps for elements undiscovered. And what's interesting was he used the patterns, things like boiling point, melting point, all of that stuff, reactivity, how easily it reacts. He used those gaps to predict future elements. So he would say, for example, in this gap, there's an element by here. It's going to have a melting point of such and such, boiling point of such and such. It's going to be very, very dense. So he predicted the properties, and later on, we found those elements and found that he was correct. So John Newlands came close, but his big mistake was that he did not leave gaps like Dmitri Mendeleev did. Okay, now moving on to why there are patterns in this periodic table. Let me rotate this. Okay, so in the periodic table that I have for you here is obviously a very shortened version of the periodic table. That's because the AQA GCSE doesn't need you to know the electronic structure of the elements past number 20. Okay, so remember when it comes to electrons that they're on the outer rings, the shells. We call the structure of where the electrons are the electronic structure, basically. And notice that as we move down the periodic table, these elements get like bigger and bigger. There's more electrons and also more shells. Now the reason why that we can't just have one shell and stick all of our electrons on that same one shell, why we need to keep adding more, is because we noticed that there's like a maximum amount of electrons that can be on each shell. Now, shell number 1 has a maximum of 2 electrons. You do have to memorize these numbers now. Shell number 2 has a maximum of 8 electrons. And shell number 3 has a maximum of 8 electrons. So it goes 2, 8, 8. So meaning once we have filled that first shell, any extra electrons we have to go on the next one. And you'll see this with lithium. So notice like with hydrogen and helium, hydrogen has an atomic number of 1. So it's only going to have 1 electron. Not a filled shell, that's fine. Helium has an atomic number of 2, has 2 electrons, just filled the first shell. And then lithium has an atomic number of 3, so it's actually going to have its first shell full, and that other third electron has to go up then to make a second shell. And then you go on, so forth, until you reach the maximum of 8, and then you have to fill the next shell then, which holds a maximum of 8. Then you have to fill the next shell. So that's how electronic structure works, because there is a maximum amount that we can fill in each shell. Now I want you to notice this pattern. Let me rub this off. I want you to notice a pattern here, because the periodic table is all about patterns. Group 0 is helium, neon, and argon. There are more, but once again, you only need to know the first 20 elements. So helium, neon, and argon. Notice that helium has 2 electrons on its outer first shell. Then neon has a filled inner shell and a filled outer shell because it's reached its maximum on the second shell of 8. Argon's the same thing. It has a filled inner shell, filled second shell, and then a completely filled third shell because it's reached that maximum of 8 again. So group 0 is very interesting. Because it has completely filled atomic shells, its electrons are happy. Its electrons have a completely filled shell. They are satisfied, so they do not like to chemically bond. So group 0 elements do not like to chemically react because shells are full. So because these shells are full, it's not going to want to chemically react with anything. But then notice the other ones, their shells aren't full, so these ones are going to chemically react. So here's the question for notes. Besides group 0, what is the relationship between group number and electronic structure? Well, have a look here. Group 1, we have 1 electron on this outer shell, then 2, and then 1 electron on the outer shell, 2, 8, 1 electron on the outer shell, 2, 8, 8, 1 electron on the outer shell. Group 2, 2 electrons on the outer shell, 2, 8, 2 electrons on the outer shell. You guys see this pattern? I'm hoping that we do see it. So the group number tells us how many electrons are on the outer shell. And if you notice that besides group 0, all of these elements here, they don't have perfectly filled shells. So they are going to actually want to either gain an electron, so take an extra electron from somewhere else, or lose their electron. Just as an example, with group 1 here, notice how there's always one spare electron just on the outer shell? Well, because that one electron is just on the outside, and that makes it a not filled shell, that atom is not happy, it's not stable, it doesn't have a perfectly filled shell. I want you guys to think having a full shell means the atom's happy. Because it has just that spare one dangling there, it's not happy about it. So, group 1 elements are very reactive. They like to lose that one electron and give it to another chemical somewhere else to form a chemical reaction because it wants to stabilize a bit more. It wants to have its full, nice shells rather than having a spare electron. So, just as a quick recap of what we've done today, we have recapped our subatomic particles, our protons, neutrons, and electrons. We talked about whether they're positive or negative or neutral. And we also talked about where they are. Now, there is a big difference between the proton, neutron, and electron in terms of what it contributes to in the atom's behavior. So with the protons, how many protons we have determines what the element is. What element do we have? The neutron contributes to the mass, and the electrons, because they're on the outside, whereas the nucleus is on the inside, because they're on the outside, they're going to be the ones that are going to be doing the chemical reacting and bonding. So the electrons have a big role to play, which is why electronic structure is important in the study of chemistry. Because if we were to study where the electrons are in an atom, we can then predict what type of reactions it's going to form. So electronic structure, it is a very, very big deal in chemistry because the electrons are the ones doing the chemical reaction. Now in future lessons, we probably only need like one more, but we're going to be going into detail specifically about certain groups. So we're going to talk about the group 1, known as the alkali metals, so the ones with the one spare electron on the outside, talk about their properties. Then we're going to also talk about group 7, and then just general trends, and then we're going to have a triple only bit by there, but that triple only bit is just short, okay? So when it comes to practice, I just want you to have a look at Seneca now because there's not much additional practice you can do. If we were to do this in class, I would have had you guys do a timeline of the periodic table's discovery and formation. So you can do that if you want, but I think what would be more useful for your time is doing Seneca or doing if you're year 9 set 1 9y1 and I teach you, I do have like a multiple choice quiz for atomic structure just for revision that's been put up for you to have a go at, just to remember protons, neutrons, electrons, what atomic number means, all of that stuff. And then hopefully we'll finish the periodic table by the time you guys have your next assessment. So remember, you don't need to submit anything to me that is not an assessment. That's every 2 weeks. And that itself should only take you 20 minutes. All right? So let me just have a look quickly at... Any questions? Okay. Yes, spot on, guys. The group number is the same as the number of electrons on the outer shell. Okay, so we're going to transition into periodic table now. Now that we had a recap of atomic structure. Recapping atomic structure was important because if I jump straight into talking about the electronic structures of the atoms, you're not going to know what I'm talking about because we did this quite a while ago. So I wanted to just recap this first. Alright? So have a go at Seneca have a go at that multiple choice quiz I put on Show My Homework. Um, and that should feed back to you what you've gotten wrong anyway. You do have 3 goes on the quiz if you feel like you can do a bit better. And those are the only things that need submitting. The only time I will ask to see what revision you've been doing is if you completely bombed a test. And then I would think, oh, hang on, I'm not sure if this person did any attempt at learning from home anyway. Okay, right, guys, have a good rest of the day, and I'll see you tomorrow. Not in person, obviously, but I'll see you on stream tomorrow. Right, bye!